the dev session today. We have 3 devs with us today. So with a developer background. So Arjay, Carlos, and Dipali. Carlos was actually my professor in college. So everything I know about coding came from him. And RJ was my colleague back in Dubai, and he was working with me in our project there. Dipali is my colleague right now at my current job. So I work with her in providing the solutions to our client here in Melbourne. And so I think just to begin, so everyone has a bit of a background of our developer backgrounds. So if the developers can just one by one state the languages that they use in their or that they're familiar with, at least, so that we have a bit of a background, and when we discuss in today's session, we know what common languages we have with each other. So from my side, I started with Visual Basic, then turned into C#, and then JavaScript, and a little bit of C++ when I was back in college. And then, so HTML, CSS, and JSON, familiar with that format. And so Arango, AQL, which is for Arango, SQL, and so on. So there may be other languages like COBOL, but very, very minimal knowledge. But at the moment, my main focus is C#. But I'm very much interested in new up-and-coming languages that they're using for front end. Yeah. So I guess that's from my side. How about you, RJ? What are the languages that you're using?
Okay. For me, currently using JavaScript. There are some other frameworks that I've been using: Angular, Vue.js, and web components. And then also I do some Node.js, a backend for JavaScript. And I have some experience also from .NET, C#, ASP.NET.
Yep.
That's all.
Okay. All right. Dipali?
Yep. So currently working with C#, JavaScript, and also knowledge about SQL Server, and also know C, C++, and Visual Basic at the college time, but not currently using that one.
Yeah.
So, okay, that's it from my side.
Okay, all right.
ASP.NET I also used.
Yes, ASP.NET. Forgot that one. Yeah. Yeah, same case for me. Yeah, it's a long time ago in my case. Yeah. Okay, all right. Sir Carlos?
Yeah, well, mostly currently I'm using C# and I did some Node.js and JavaScript for that, but not as often, but it's just other languages. So their languages, they're pretty old already, right? But I've been actively using them, like Java stuff.
Yes, actually.
Okay.
Yeah, I feel the same about C#. Everyone's talking about the new JavaScript frameworks.
Yep.
So and Python, especially Python.
Yes. Python, Python, a little of Python because I need to debug some open source stuff.
That's cool. That's cool. All right. Okay.
Okay. That's.
All right. Thanks, guys. So yeah, let's start now with. This is actually a very quick crash course into neurUL. So we have 40 minutes, and we'll just try to go through neurUL as quickly as we can, and this will be the basis of our succeeding sessions for the developer aspect of neurUL. And yeah, so let's begin. And as always, feel free to interrupt me. Let me know if you have any questions. If you think something is not clear, just let me know, and share your thoughts with everyone whenever you can or whenever you want. Right? Okay. So everyone, can you see my screen? Just let me know if you can see my pointer as well. Let me just turn on my pointer.
Oh, good.
Okay.
Wait,
Right. Can you see my pointer?
your
Yes.
mouse.
Yeah, my mouse pointer. Yeah. Okay. All right. So
Yeah.
the neural syntax. The neural syntax is available from the website of neurul.org. So you can just view it there. Just get my mouse pad. It's easier to use this mouse. All right. So you can view this from neurul.org itself. So in the neural section, I think in the page syntax. Okay, but it's easy to find. You can just browse it there directly if you want. Now, the syntax currently has, in the current version, which is version 1, has only 11 points that you need to be familiar with to be able to encode in neurUL. So we'll go through them one by one, and we'll just explain a bit what's inside. Okay. So the first one is, this is for the general terms. So points 1 to 8 are for neurUL in general. So a neuron may have a tag value, which may be used to define it or to refer to a specific concept. So we use a tag value to define a neuron independent of its relations with other neurons. So it's like abstraction, or it's like when you're defining a class or defining a property. So this is the tag. So in this case, let me show you how it looks like in neurUL itself. So as you can see here, the neurons that we've created, we've basically added a tag to each of them, right? So the user, it's up to the user if they want to detail these neurons by creating the connections with one another, or just leave it as it is. So just create a name for it. So imagine if it's like the human brain. It's like you have the neural network in your brain, but then we just add a tag or a name, so it's easy to identify or to differentiate our neurons, right? So that is how you basically define a neuron, just by tagging it. So that's the first one. The second rule is that a neuron may have at least one terminal. So in the case, for example, of the robot poodle, just expand that. So by the way, I'm connecting to my server at home. So my digital brain is at home, okay? So in this case, robot poodle, I've created 3 different terminals or axon terminals for this neuron. So we have robot, poodle, and then animal. All right. So that's basically what a terminal is. You can have any number of terminals, and you may have at least one. So that's one-to-many relationship between a neuron and the terminals. Okay. A terminal links the neuron that contains it, called a presynaptic neuron, to exactly one other neuron called a postsynaptic neuron. So in this business rule, we're just saying that this terminal here links a neuron to exactly one other neuron, right? So you can't have a terminal that connects to multiple. A terminal links the neuron that contains it, called a presynaptic neuron, to exactly one other neuron called a postsynaptic neuron. So these are the postsynaptic neurons, and this is the presynaptic neuron. Now, number 4, linking enables neurons to define one another. So using linking that we defined in number 3, we're able to use other neurons to define another neuron. So as you can see here, we can say there were 2 ways of defining this neuron here. One is by tagging, and one is by connecting them to other neurons using axon terminals, right? So even if we remove the name robot poodle from here, let's say even if we remove it, we know that this neuron is actually these 3 neurons combined, So that's how you do it via linking. Now, each neuron has a voltage which is normally at resting potential. So that's negative 70 millivolts. So if you went through the previous sessions that we had, we discussed how the actual potential works. So if the voltage of a neuron changes and reaches what is called a spike threshold, which is negative 55, a spike will be generated by the neuron. So in this case, if I spike this neuron and it only requires one spike to fire the other neurons, then the spike will be generated by this neuron, and then it will spike the other 3 neurons. So that's basically the theory that we were discussing in the first session, wherein to be able to replicate the same perceptions that were spiked when we were seeing something, all we need to do is to spike the same exact neurons. So without seeing these specific neurons, or without spiking these individual neurons as if we are seeing something, all we need to do is spike a grandmother cell. So the exact same perceptions are spiked. So if you would go back to the example that we had for Jennifer Aniston, to be able to spike all of the neurons related to Jennifer Aniston, all that we need to do is to create a grandmother cell for Jennifer Aniston, so that when you spike Jennifer Aniston, all of the attributes related to her will be spiked at the same time. Okay, so that's basically the point of number 5 and number 6. So for number 6, a spike is an impulse that travels from a presynaptic neuron to its terminals and then to the linked postsynaptic neuron. So that is what a spike is. It is an impulse that travels from here, which goes along the terminals and then goes and is forwarded to the postsynaptic neurons. Okay. When spiked, so this terminal here, when it is spiked, it may either further excite or inhibit the spike of a postsynaptic neuron. So you can see that here. So the color represents the behavior of, actually, that is actually the effect here. So if you go here, you will see that the effect of robot poodle to animal is inhibit. The effect of robot poodle to poodle is excite. And to robot, it is excite. So what does that mean? If you spike robot poodle, what will happen is it will excite the perceptions of robot and poodle, but it will inhibit animal. Okay, because if we expand animal, and if we further go through the relationships of animal. Oh, okay. So it's basically saying, let's just expand dog as well. Right. So we're basically saying that robot poodle is a robot and a poodle is a dog. A dog is an animal, but in this case, our grandmother cell says that it's not actually an animal. So that's why we inhibit this cell here. Okay. So this is like in coding in C#, this is how you achieve suppression of certain attributes that you override from your base class. All right, so that's a similarity that we have. For example, in C#. In C#, what we do is we hide those members. But in this case, instead of just hiding, we are actually suppressing the excitation of that neuron. Okay. Now, okay. The next one is the degree to which the action of a terminal may affect a linked neuron is called the strength of a terminal. So it can be 33%, 50%, etc. So the default value is 1. But if, for example, it is 0.33 or 0.5, then it will require a combination of neurons to fire before that specific neuron is fired. So you will remember this in the discussion that we had about the interneurons in the first session. So to be able to fire call a friend or increase volume, then you require 4 inputs to that neuron for that to be fired. Okay, so in neurul, in the code of neurul, you may also use that to retrieve values, but that is actually part of the actions topic, and we'll discuss that later. So that's how you combine different inputs to stimulate certain neurons. Okay. Now this is the most, I think this is the most important, these are the most important parts. So these are the general rules for all types of neurons, whether they represent perceptions or actions. Now, the following two are specific to perceptions only, okay? So if a neuron generically defines an indefinite number of other neurons, then the former should postsynaptically define the latter. These are called intentions. So in this case, an animal generically defines a robot, a dog, right? If you're going to create another example of something which generically defines an animal, let's say a cat. So let's create that neuron. Okay, so apparently we already have a cat in the system. Okay, let's add that as an animal. All right, so we just add that to animal and just use the defaults for this. Right, so if we expand animal again, we now have the cat here. And a robot poodle is actually, yeah, a poodle looks like a cat, so that's why we have this. So we can say that this is an illusion. So let's just expand this further to make it easier for you. Right. So if a neuron generically defines an indefinite number of other neurons, then the former should postsynaptically define the latter. All right. So an animal is an intention, a logical intention of a cat and a dog. Okay. So this is a shared attribute of both a cat and a dog. So that's why we configure it so that it is called after these neurons are called. So that when you say, okay, I want to think of a dog, then when you think of a dog, immediately you spike animal. If you think of a cat, then it spikes animal. All right. There are other attributes like location, and size, and basically properties, right? So that's how you define those things in neural. So you create a postsynaptic relationship with a presynaptic neuron. Now, if a neuron specifically defines another neuron or cumulatively defines a set of other neurons, then the former should presynaptically define the latter. So these are called extensions, logical extensions. So a cat is a more specific type of an animal. So that's why we put it as a presynaptic neuron. A dog is a more specific type of an animal. So that's why we create a presynaptic neuron here. Okay. Now, in neurul, not like in other languages like C#, we encourage multiple inheritance, and we use that to our advantage. And it is actually behind the idea of sparse coding, which we'll go through in a while. So sparse coding is a theory about neural encoding, or a hypothesis. It's not proven yet, but it's the thinking that, you know, just like objects, when you're coding or in programming, you reuse as much as you want, or as you can, to be able to create code and reduce redundancy at the same time. So we can have the attribute of, for example, size. And we know that all three-dimensional objects have size. So size can be an attribute of an animal. It can be an attribute of a building or a planet or a moon, for example, whatever has size. So unlike in C#, for example, when you create a class for an animal, you have a size, you have a height, right? And you define that property as only part of that class. In neurUL, since you're able to reuse as many terminals as you want, then you can define as many classes as you want, and then all of those classes can point to the same attribute called size. So you don't have to have a redundant set of properties that you have to reuse everywhere. All right, so we'll show that in a while as well. And that's why we say cumulatively defines, because we combine attributes together. Okay, so for example, robot poodle is actually a combination of robot and poodle. So that's why we have robot poodle. All right, so was the section on perceptions clear? Do you have any questions? Is there something that you think I need to clarify further?
So far, none.
Okay, all right. How about the others? Yep.
So, yeah, I think it's okay.
Cool. All right. Okay, so now for the actions, it's very simple. This is, if you remember the session, the first session, so if you combine inputs, then, okay, let's just read it first. If a neuron defines a response to another neuron, which defines a stimulus, then the former should postsynaptically define the latter. Neurons that link stimuli to responses are called interneurons. So let's say the owner of this brain loves cats, okay? So what we'll do is we'll create a response so that, okay, let's just create something here. Let's create two responses first. One is cuddle, right? One is cuddle. Okay, sorry, I have some breakpoints running in my code. Yep. So, and let's say the other response is go home, go away, okay? So let's say that this person loves cats. Now, all we need to do is say that when it sees a cat, okay, let's, when seen, let's say, we have another sensory input, let's say see, okay? Okay, so let's say see cat, and let's say see dog, and let's say see tiger. Okay. No, cancel. I think it's not right. I think I did not code it correctly. Yeah, it did not code correctly. I think they did something wrong there. But let's see, dog, if it works. Yeah, I think it's not right. All right, sorry about that. This should not call dog, actually. This should not call these directly. So ideally, okay, let me just do it properly this time. So, all right, let's create an interneuron first. Okay, my bad. So, yeah, okay. We then need to create an interneuron here. So let's say C dog, right? Which basically combines the input of the inputs of C and dog. So C dog is actually C, and it has to have an effect of 1, which excite, and a strength of 0.5. Yeah. So, and then dog should call C dog as well. So the effect is 1 and the strength is 0.5. Right. Right. So as you can see here, if we expand this further, these are the stimuli and this is the response. This is the response here. So when a C event happens, then this interneuron is called. When this event happens, then this interneuron is called. And let's say when we see a dog, let's say if that is the stimuli, then we want to create a response wherein go away happens. Then just use the defaults. So what will happen is, if this is spiked, is robot poodle is spiked, and then C is spiked, then you will see that the action potential will cascade to the point that go away is triggered in the end. So if we have an application or software which just listens to spikes of certain specific neurons, then when this brain detects this input, and when finally this neuron is spiked, that application or client component will cause the brain to go away or move away from the sense or from the source of the sensory experience. All right, and then we can create an alternative action for cat. So when cat is seen, we create an interneuron for see cat, and then it will go and do cuddle action. All right, so as you can see, this syntax here allows us to create, allows us to start with very basic data formats. And at the same time, we're able to define behavior and actually create executable code through abstraction and sparse coding. All right. Were there any questions about perceptions, stimuli?
It's good.
That's good? Clear?
Yep.
Okay, all right. Okay, so let's have a look at now the comparison with C# section. So the main theory, if you'd like to check it further, is sparse coding. So this is one of the building blocks, basic building blocks, and this is currently being researched in neuroscience. They still haven't been able to prove it well, but it's actively being researched, and that's what we're capitalizing on in neurUL. So we're using software to simulate neurons to see if actually this is the way our brains are doing it. Then the next concept is abstraction. So even in, I've seen a lot of neuroscience articles, and I can send it to you later if you like. And they're thinking that this is how we're really doing it. Basically, we're combining ideas on top of one another to come up with more complex ideas and so on. So that's abstraction there. All right. So if we compare it with C#, classes, as we said earlier, we are able to define classes using the concept of by creating specific neurons to define these classes. Okay, I just have another example that we'll use for this purpose, and this is based on the linguistic effort that I've been working on previously, wherein we define classes for certain elements of language. So we won't go through the details of how this is interpreted right now, but we'll just go through it very quickly, and I think we'll need a separate session to go deeper into how we use neurUL to represent language. This will actually be part of the human language track of neurUL, so we'll go into it there. So as you can see here, we have defined classes such as structure, a head, and indefinite or article. So in English, what are the articles? We have the, a, an, and so on. We have prepositions, right? And there are types of determiners. So as you can see here, we implement inheritance using just the inherits neuron. So here, I just didn't expand inherits here, but this actually connects to inherits. So everything that needs inheritance just needs to connect to the neuron inherits. And then using combination, we can say that if anything needs to inherit from an article, then it just needs to connect to this neuron here. So inherits article, we create a neuron here. Inherits from endocentric meaning, we create this here. If you want to inherit from a determiner, you combine inherits and then determiner. So that's how we achieve inheritance. So if we say inherits animal, so let's say this is animal and this is inherits, you just combine those two so that you have inherits animal. So let's say this is dog, inherits animal, this is animal, this is inherits. So what does that allow us to do? By spiking dog, we know that it is an inheritance of an animal, right? Okay, so that's inheritance. How do we achieve instantiation? So for instantiation, you just similar. It's very similar to inheritance. We just connect to a neuron called instantiates and then indefinite. So what are two examples or instances of indefinite articles? An and a in the English language, and even the, right? So if you think about it, if you think of the word an, what will happen is an will spike this neuron which says that it's an indefinite instance of an article which is a determiner. So you can see this whole thing, this whole track is immediately a sentence of information. It's already a statement of information. And you can read the same thing over and over again. So it's like the turtles all the way down, you know? So it's all abstractions all the way down. So what is endocentric meaning? For example, endocentric meaning is an endocentric structure which inherits from structure and it has a head. So that's how you read it. So you can imagine building more and more complicated systems on top of one another and basically using neurons to achieve that end. Okay, so we have instances, as we just mentioned. So you can have an instance of a dog, so let's say Barney or whatever. So you can have records. You will achieve the same thing that you do with SQL. You define a graph network using the neural structure to define your whole database. And what it allows you is it solves one of the main problems in shared databases. If you're familiar with the challenge that they have in shared databases, the main problem is when you define a shared database between different systems, then what if there's a change in the schema, right? So you will affect the schema or all of the dependent components in your shared database. By using this neural structure, it becomes ultra flexible, if you will. So you can have you can use eventual consistency, which is a concept in domain-driven design. You can use that to your advantage. So you're not restricted by the fact that your schema is only meets requirements for specific components that use your database. What you can do is you can gradually update your data so that specific records meet requirements of specific components, and then gradually upgrade or update your code so that everyone is in sync. All of the client components are in sync, just like your human brain, right? There are memories that we have that aren't yet fully adapted to certain requirements. And what we do is, while we sleep, while we go about our daily lives, we update our memories and consolidate them. And then later on, after some time, we realize, oh, okay, that makes sense. So that's why that is an instance of that, or that is an instance or a type of this. So we use eventual consistency to adapt our memories as we go through our daily lives. Okay, were there any other questions before we proceed to an additional concept?
No.
That's fine, okay. All right, so refines, this is a special concept that I only found to be necessary in neurUL. Refines is basically using a more specific version for a property. So let's say, I'm not sure if it's a very easy to understand example, but yeah, let's give it a try. So refines here, okay, right. Refines determiner head and a head, okay, right. So a determiner head is a type of linguistic construct wherein a determiner is used as the head of a dependency tree. So for example, the quick brown fox, right? The quick brown fox, in the sentence, the quick brown fox jumps over the lazy dog. So let's say the is the determiner, right? What happens is determiner is a generic version of the, right? Now in this case, in this example, a or a is a type of determiner, right? So we are just saying that this determiner head can be inherited by anything or can be refined by anything whose parts specialize one or both of these parts. So in this case, determiner head, a head, is actually a refinement of determiner head because a is a specialization of determiner. So you say determiner, as you can see here, a is a derivation of determiner. So a head is basically a refinement of determiner head. Another example of refinement is must have determiner head. So it's in C#, for example, when you create properties, they are fixed, right, in the code. But in neurUL, you can refine them as you want. So must have determiner head. Let's say this is a property, right? Must have determiner head. It can be must have a head. It can be must have many heads. It can be must have all heads. So you can refine your data elements as many times as you want. You can reuse them as many times as you want using refines, right? So this is different from instantiation. This is different from inheritance. This is basically enhancing or creating a derivation of an element using other derivations. All right. So it's like a generic property, similar, but I guess more flexible. Okay, is that clear? there any questions about that?
So far.
Okay, cool. All right. So, okay, I think we'll just be over by 10 minutes. Sorry about that, guys. Huh? I just try to make this fast. So just 10 minutes more. So again, okay, so actions, we went through this already. So we have conditions. We were able to implement conditions using neural code. So if we see a dog, then see dog, go away. If it is a cat, then cuddle. Right? So we're able to implement conditions using different neural pathways or action potential, or they call it spike trains. That's the proper term for it, spike trains. Okay, so let's just go over some of the main concepts that we need to understand to be able to work with the neurul as a developer. Domain-driven design is very important because it emphasizes the importance of a ubiquitous language. So that's the reason why we try to mimic the natural design of the neural network as much as possible. So all the terms that we've been using so far have been faithfully copied from neuroscience. And what this allows us is it allows us to communicate with neuroscientists in the future, or to anyone who wants to work with our solution. And it also allows us to simulate and mimic and replicate the advantages of the natural design, which has been time proven and field tested for hundreds of millions of years, as we know. So domain-driven design is an important thing, and one of a very good book that I studied for it is the Implementing DDD by Vaughn, Vernon Vaughn, I think is the full name. Vince Vaughn is a comedian. I don't know where that came from. All right, so within this topic, you will find event sourcing and command query responsibility segregation. Those are very important topics because it allows us to design our application or neural in a sense that is safe for and open to changes. So if you see the design, the data that we have is just events. It's just a list of events that it goes through. So you can then regenerate your brain or rewind it back to a previous state as easily as you can. And so that gives you a layer of protection, because if there's a problem with the data, then if it gets corrupted, for example, or if the user of neural finds that his state has been corrupted, then it's just a matter of rewinding back to a previous state, let's say at event 30 back in July 14, so that all of the events will then be truncated after that. The next important topic is command query responsibility segregation. So all of our microservices have two parts. One is the input port and one is the output port. So it will be easy for us to allow clients of our APIs to just differentiate between the ability to write or to read data. Okay, so that's because we separated the write components from the output components. Okay, now microservices is an important concept because it allows us to reuse and to modularize our components. So changes in one don't easily affect the others. The only thing that I think is a violation, and even if you Google it, a lot of architects are against it, which is the shared database. They're saying that the shared database approach is not safe because in practice, you have a shared database in the background and you have all your components using the same database and so on. From our neural's perspective, the answer that I think is relevant is that how does the brain work? I mean, we have a shared database which serves as our brain, and that's how we're able to consolidate so many different sources of information. And so it's still an ongoing experiment, I would say. But if it works out and we're able to prove that the natural design is optimal, then I guess that's the only way to really see if the natural design is how it should be. Okay, so I guess what I'm trying to say is the reason why there's a resistance to the idea of a shared database is because I think of technological constraints at the moment wherein adaptation and flexibility of your schema is not that achievable considering the current designs of in IT, in information technology. But should there come a time wherein we have neurons to represent our data, I think it will be much easier to adapt and implement. Then the next important topic is the hexagonal ports and adapters. So it's a rather large topic, but basically the idea is that we have these components that can plug and play, with each other and with different types. So the cortex, for example, which is the recorder of events. So when you add a neuron, when you modify a tag, when you add a terminal, so the cortex handles that. Now we are able to define as many inputs to this in port. So you can have different senses, you can have different sensory components, you can have different writers, you can have log files writing to this in port. And we are able to achieve that using the ports and adapters approach. So these are microservices which are independent of one another. Right, so let's just go through the components now. Sorry if I'm rushing it a bit. I'm just trying to catch up. So the main component in neurUL is the server. So this server can host any number of avatars. So avatar is basically a digital twin of your person. So I can have an avatar for work. I can have an avatar for school. I can have an avatar for anything, for sports. And then each of those avatars will have different brains or its own brains. So my avatar for work will have its own brain. My avatar for home will have its own brain, and sports and so on. So by having its own brain, we can obviously connect different sets of sensory inputs to those brains. So that's why the avatar concept, that's what the avatar concepts allows us to manage. So the avatar, think of an avatar as your body or your digital body. And then that body will have a brain, which is the cortex, memory, image, identity access, and cortex updater. And then you will have your organs that you will connect to that avatar. So you can have motion sensor. You can have Facebook logger. You can have your Chrome browser. History logger, right? So these are apps that we can then create that will all synchronize with your cortex. So all of the activities for each of these organs write directly to your cortex. Okay, so this is your body, and these are the parts of your body. And since an avatar is part of a server, you can have as many avatars in each server. Okay, so the brain has a cortex, which is your cerebral cortex. This is where your neurons reside. It simply listens to commands, to modifications to your neural network. The out port basically broadcasts events or events in your neural network. So if something is added, if something is removed, something is deleted or changed, this out port basically announces that or serves notifications for those events. Cortex graph is basically generating a graph database based on the events coming from the cortex. So if you call regenerate, for example, it will grow your brain for you as quickly as it can. And the out port basically serves the neural network. So when we are browsing neurUL, for example, every time I expand a neuron here, it's actually making a call to the neural graph to obtain the neurons related to a specific neuron. So it's a REST API, and that's what we use to serve the neural network. So as you can see, this is where the commands are, and this is where the data is coming from. So that's where the CQRS is implemented. Now the memory image is going to be the spiker. So this is, you may do a separate search for this. This is the idea that you host everything or the whole brain in memory. So at the moment, this network here uses the graph or the Arango database to retrieve the neural network, right? Memory image is the idea that we don't need a database to store the neurons. So what will happen is this memory image will just query all of the events, and it will run a brain simply in memory. So you can imagine Jarvis, you can imagine an actual brain running in the memory of your computer. So if you are familiar with that, Arjay, I'm sure you are. In our previous project, we had a simulator, an ATM running in the memory of the machine, right? So that is actually what we're going to do in the memory image component. We're going to run a brain in the memory of your PC. Okay, and so that what that allows us to do is we can then spike specific neurons, and then we can get in real time responses to some neurons or to the neural network. So if we spike C and dog, we immediately get the response go away. So the data becomes the actual code of our applications. The other component which we need to do is the identity access. This is the OAuth provider, and this component will use the neural network to determine who's allowed to access this neural network. So let's say Dipali or Michael has read access rights as defined by the neuron, then cognition will use that information to determine if that user can log into this brain, right? Because what we can do is this brain can actually be your Facebook profile, for example. So when you want to share this neuron and you want to share your experiences, it will just be a matter of sharing a brain and defining which users can access your brain. And we'll use popular technologies at the moment to secure this profile or this network. All right. Now the Cortex updater is an important component because the responsibility of this component is to update your data structure. So that's what I worked on. Actually, that's what needs to be worked on quite soon, because I worked on something very similar or something very much related in the past few weeks. I had to update the data structure so that the neuron is separated from the terminal, so that if there are heart rate values which are quickly being saved in the system, it will be able to adapt itself. So I had to change the structure, but the problem was I can no longer read from the previous data structure. So what the Cortex updater will do is it will update the structure through time, through different schemas of the neural network. Right? But we don't expect a lot of changes to this structure because we're really just mimicking natural neural networks here. So we're hoping that these structures will stay the same, unless, of course, humans evolve or something, and we find something that we haven't considered yet in the neural design, like astrocytes and so on.
Okay.
Yeah. Then the organs. This is the heart rate monitor. These are the apps which surround the brain. All right. And this is the Neural Studio. This is the app here, right? We currently have a Windows-based neural network designer. And what we badly need is a web-based designer, so that users from Apple, I've been talking to some users who only use Apple as their work machines. So it would be good if we have a web-based neural editor, so that we'll be able to use any platform, really. So I guess what would be good is we develop these side by side, and then we can see then, what we can, how we can improve the design of each platform to work with neurul. And yeah, I think we can just go through quickly the roadmap, and then we'll go in the next session. We'll just look at the details of the backlog and the tools that we use for development. So for the roadmap, I think it's highly important to look at the server now, because that will allow each user to share their own brains, and so that they can start using it for their own purposes. In my case, I'd love to be able to use it to manage the tasks related to neurul. And the only reason I'm not able to share this right now is because if we have like 10 users using this network to manage tasks, to use it for Jira or like an Asana for tasks related to neurul, then it will be a chaos, because we don't have a way to know who made what change. So I think the identity server is important, as well as the spiker. This will allow us to automate responses in Asana or in neurul, and this can be used in the heart rate monitor and the different apps. I remember Michael in the NL, natural language processing. That's where the spiker will come in. Then the reactor, that's part of the heart rate monitor. We'll go through that later on. Then the illusion validator. So this basically validates your instances in your inheritance trees, so that you're able to make sure that when you say, let's say, this is an instance of something else, or an inheritance of something else, this validates and makes sure that it really is an instance or an inheritance of a more generic neuron. So it's like, it will show you compilation errors, so to speak, in software, in mainstream development. So it will validate your data for you, let's say while you sleep, or it will do it in the background to check that your data is consistent. And it will then allow for eventual consistency for your data. The next very important initiative in neurul is the neuralnet, neurul.net. So neurul.net is basically the creation of it's the creation of a core language or a core dictionary for neurul, so that we will have a brain for neurul.net, and all the users for neurul will reference that brain. So we have common definitions in the internet. So you don't, let's say for example, I shouldn't need to define a concept from scratch. If, for example, I want to use a note, or let's say I want to define a task, then I should just reference the definition of task in the internet. And then that should make it easy for me to define a task list. So that's what the neurul.net is for. So this is primarily language-based, and it's really just a matter of creating truth tables or truth networks, which are commonly defined among all users, right? And we've discussed the platform already. So these are the efforts that we need to look into, so that we're able to support web and Windows and possibly Mac. And then Fibonacci will look into the next session. And the apps that we're looking at right now is the heart rate monitor and a very simple GPS tracker, which will save all of your GPS locations in your brain, so that you can then rewind to a specific point in time, let's say 2014, February 5, and know exactly your locations at that time, which is something that Google Maps is doing already, but it's storing it in Google servers. And you're not able to integrate it with any other aspect of your life easily or natively. And by using a neural network like this, you can then store a date, a location, and then you can link that to any data element that needs to be associated with that. Okay, so yeah, that was definitely a crash course. Apologies if that was too fast.
Yeah, it's okay.
That's okay. That's great. That's great. Were there any questions from everyone? From anyone?
None for me.
Okay.
All good. Loving it.
Sorry, Michael.
Loving it. All good.
Okay, cool. Perfect. Papa, Carlos, were there questions? Is everything clear? All right. I think that's great then. Yep. Sorry, Carlos.
Yeah, it's pretty logical.
Okay. Thanks for that. All right. I think that's it. That's it for today's session. There are no further questions. I think we can close, and just feel free to provide your comments in the chat or in the Slack channel, so we have it consolidated there, and we'll base it on. I think we'll have another session either mid next week or next Saturday, and really the intention for this session was to enable any developer or anyone who wants to contribute as a developer to start working with neurUL. And thank you so much for attending, and have a great rest of the weekend.